Hello students, good time to all. I am Chandan Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss another applications of Maxwell's thermodynamic relations, that is values of Cp minus Cv. Let's begin. Cp minus Cv. Cp is the specific heat at constant pressure. Cv is the specific heat at constant volume, which is further known as the Mayor's formula. That is further known as the Mayor's formula. Now we calculate the Mayor's formula by using Maxwell's thermodynamic relations. So here we define we have defined Cp, that is specific heat at constant pressure, del Q by del T at constant pressure. In place of dQ, I write TdS. We know dQ is equal to T ds, that is from second law of thermodynamics. So that equation will be T del S del T at constant pressure, and Cv specific heat at constant volume, del Q by del T at constant volume, that will be T del S by del T at constant volume. Since we know entropy S in a perfect differential and is a function of temperature and volume. Entropy is a function of temperature and volume. Therefore, we can write, since it is a perfect differential, so ds is equal to, that is del S by del T at constant volume dt plus del S by del V, del S by del V at constant temperature dV, or ds by dt will be how much? We calculate ds by dt, let at constant pressure. What we find? That term will be ds by del T at constant volume, dt by dt cancel out, plus del S del V at constant temperature and del V del T at constant pressure. That equation. Now here we have to apply Maxwell's second thermodynamic relation. So we know that from Maxwell's second thermodynamic relation, del S by del V at constant temperature is equal to del P by del T at constant volume. So in place of del S by del V at constant temperature, we write del P by del T at constant volume. So that equation changes to, that is del S del T at constant pressure is equal to del S by del T at constant volume, plus in place of del S by del V at constant temperature, we write del P by del T at constant volume. So it will be del P by del T at constant volume, then del V by del T at constant pressure. Now multiplying T on both sides, T del S by del T at constant pressure is equal to T del S by del T at constant volume plus T del P by del T at constant volume del V by del T at constant P, where we multiplying T on both sides. T del S by del T at constant pressure, T del S by del T at constant pressure, that is Cp. So that result will be Cp is equal to T del S by del T at constant volume, T del S by del T at constant volume, that is Cv plus T del P by del T at constant volume, then del V by del T at constant pressure. Now Cp minus Cv is equal to T del P by del T at constant volume and del V by del T at constant pressure. Let equation number 1. By using that equation, we can find out the result of Cp minus Cv in case of perfect gas, in case of van der Waals gas, and also in case of any substance. So first one, for perfect gas, what is the result of Cp minus Cv? For perfect gas, we know perfect gas, that is also known as the ideal gas, perfect gas, or we can say that is the ideal gas, perfect gas or ideal gas. What is the result of Cp minus Cv? For an ideal gas, for 1 mole, for an ideal gas of 1 mole, the equation is Pv is equal to RT. Pv is equal to nRT, since we consider 1 mole, n is equal to 1, so Pv is equal to RT. Our aim is to find out what is del P by del T at constant volume and what is del V by del T at constant pressure. Then we get Cp minus Cv. So now we check what is del P by del T, at constant volume. In that of particular equation, so del P by del T at constant volume will be R by V, and del V by del T at constant pressure, so del V by del T, that means differentiating that with respect to T, first dV, so it will be del V by del T at constant pressure, del V by del T at constant pressure, we get R by P. Now putting these values in equation 1, so what we have? Substituting these values, or we say putting these values in equation 1, we get the Cp minus Cv is equal to T, that is R by V into R by P. That is dV by dt, that is R by V, that is R by P. So here that is T R square by Pv. Look at that of equation, Pv is equal to RT, so in place of Pv I substitute RT, that is T R square divided by RT. Now 1 R cancel out, 1T cancel out, it will be R. So Cp minus Cv is equal to R. which is the Mayer's formula for ideal gas. That is the Mayer's formula for an ideal gas. This is the result of Cp minus Cv is equal to R for ideal gas or perfect gas. Now, result of Cp minus Cv for van der Waals gas. Next, for van der Waals gas, we take Cp minus Cv. For van der Waals gas, we have to calculate the result of Cp minus Cv. Again, we have to consider 1 mole of van der Waals gas. For a van der Waals gas of 1 mole, the gas equation is, that is P plus A by V square V minus B is equal to RT. Our task is to find out del P by del T at constant volume and del V by del T at constant pressure. So, how we have to calculate this two one? Therefore, from that of equation we take P plus A by V square is equal to RT divided by V minus B. Now, differentiating that equation, we take that as equation number 1, that as equation number 2, and differentiating this, equation 2 with respect to temperature T at constant volume. What we get? Differentiating with respect to temperature at constant volume. So, the result will be del P by del T at constant volume is equal to R divided by V minus B. That is the result. Again, differentiating that equation number 2 with respect to temperature but at constant pressure. Again, differentiating equation number 2 with respect to, here I take equation number I and double I. So, here equation number double I, as we before we take equation number 1. So, differentiating equation number double I with respect to T at constant pressure. So, what we get? That equation with respect to T but at constant pressure, it will be minus 2A divided by VQ as V square minus 2 V to the power minus 3, that will be minus 2A divided by VQ del V by del T at constant pressure is equal to that term. First that at the constant, then the term will be RT divided by V minus B square del V by del T and constant pressure plus R divided by V minus B. Now, RT divided by V minus B whole square del V by del T at constant pressure minus 2A divided by VQ del V by del T at constant pressure, again that term R divided by V minus B, or del V by del T at constant pressure taking common, del V by del T constant pressure taking as common, RT divided by V minus B whole square minus 2A divided by VQ is equal to R divided by V minus B, or del V by del T at constant pressure is equal to R divided by V minus B whole divided by that term, that is RT V minus B whole square minus 2A divided by VQ. We get del P by del T at constant volume and del V by del T at constant pressure. Now putting these values in equation number 1 here. So what we get? Now putting these values in equation 1, we get, so Cp minus Cv is equal to T into, that is del P by del T at constant volume, that is R divided by V minus B, that is R divided by V minus B into del V by del T at constant pressure, so R by V minus B whole divided by RT divided by V minus B square minus 2A divided by VQ is equal to, that is T into R square divided by V minus B whole square. In that bracket it will be RT divided by V minus B whole square taking common, so 1 minus 2A V minus B whole square divided by VQ into RT is equal to, that is R, this is the common term, okay, this is the common term inside that bracket, so that term cancel out, only R exists here, TT cancel out, V minus B square cancel out, only R exists. So in that bracket 1 minus 2A V minus B whole square divided by VQ RT to the power minus 1. Now expanding that term binomially, or first we simplifying that one, we write here R 1 minus 2A V square, here neglecting B, why? Just write it, VQ RT to the power minus 1. Why I neglect B here? So you know, since the Van der Waals constant, B, which is known as co-volume, is very small, as compared to V, the volume. So we neglect that one. So we neglect B. Now expand it binomially. What we have? We get R 1 plus, here 1V cancel out, only V in that of denominator exists, so 2A divided by V RT applying binomial theorem, and neglecting the higher power of (2a) divided by VRT, 2a divided by VRT, that term. Here 1V cancel out. So finally we get Cp minus Cv for Van der Waals gas is equal to R whole into 1 plus 2a divided by VRT, that for Van der Waals gas. Now we take any substance and derive what should be the value of Cp minus Cv. Now we take any substance. For any substance, what should be the value of Cp minus Cv? We have derived the relation for Cp minus Cv for an ideal gas and also for van der Waals gas. Means we say the Mayer's formula for any substance, whether it is solid, liquid or gas, can be derived. So, in that of case for any substance, we define, here we define two things. One is isothermal, we define isothermal Bock modulus of elasticity and the coefficient of cubical expansion of any substance. We define these two one, and then we can easily find out the result of Cp minus Cv for any substance. So, what is first one? That is isothermal Bock modulus of elasticity. Means isothermal, here temperature T are constant, and we calculate the Bock modulus of elasticity. So, the Bock modulus of elasticity of any substance for isothermal process let me define EI, Bock modulus for any substance in isothermal process. Let me define EI, which is defined as, that is EI is equal to increase in pressure divided by change in volume to original volume. Increase in pressure, that is dP, change in volume to original volume, that is dV by V. That can be written as minus V dP by dV at constant temperature in case of isothermal case. And here we implement the negative sign, because because increase of pressure, with increase of pressure results decrease in volume decreases. Increase of pressure results decrease in volume. This is first one, that is the modulus of elasticity of any substance for isothermal process. Now, the coefficient of cubical expansion of any substance, let me define also coefficient of cubical expansion for any substance gamma is defined as gamma is equal to change in volume to that of original volume into rise in temperature. Original volume into rise in temperature. That is change in volume del V, original volume V, rise in temperature del T, at constant pressure it is defined. So we write gamma equal to 1 by V del V by del T at constant pressure. Now we get del V by del P by del V at constant temperature, del P by del T, our task is to get del P by del T at constant volume and del V by del T at constant temperature. So how we transform to that form? So we have to introduce the relation here. As we write, we know Cp minus Cv is equal to T, that is del P by del T at constant volume into del V by del T at constant pressure, that is T. In place of del P by del T at constant temperature, sorry, at constant volume, del P by del T at constant volume. Now what we take here? We change it. We write that is del P by del V at constant temperature and del V by del T at constant pressure. So there will be no such change, means del V cancel out, so it will be del V del V. So here I take the negative sign also. Now that is del V by del T at constant pressure, that term. These two terms are multiplied, so here we get T minus del P by del V at constant temperature, it is square of del V by del T at constant pressure whole square. The term Cp minus Cv is always positive, because the slope we know del P by del V at constant temperature is always negative, and the slope can be positive, that is can be positive or negative. So that square is always positive. So we can write here Cp minus Cv is equal to T, in place of minus del P by del T del V at constant temperature, del P by del T at constant temperature, that is EI divided by V. So EI divided by V. Next its square, that is gamma V square, or Cp minus Cv is equal to T gamma square V, 1V cancel out, so 1V exists, into EI. That is the result of Cp minus Cv for any substance. For any substance we calculate Cp minus Cv. So with the help of this video lecture, we understand another applications of Maxwell's thermodynamic relation. With the help of Maxwell's thermodynamic relation, we calculate the value of Cp minus Cv, which is known as the Mayer's formula. First we get the relation, and for ideal gas or perfect gas we take Cp minus Cv is equal to R. Then for van der Waals gas we find out Cp minus Cv, and finally for any substance, by defining these 2 points we get the result of Cp minus Cv. So with this useful and informative notes, let me wind up this session. Thank you.